When organizations migrate data to a multi-tenant cloud, an architecture where a single software instance serves multiple distinct customers, they exponentially increase their attack surface. To manage this massive surface area, we rely on the CIA Triad, an information security model forming the baseline for protecting all data. It stands for confidentiality, integrity, and availability. We define security as a mathematically rigorous state, governed by calculated boundaries. Every breach represents a specific violation of one or more of these three axioms. Without a strict framework mapping potential threats directly to the CIA Triad, a distributed cloud network is inherently vulnerable. In this lecture, we will build that framework by mapping the 4 fundamental attack vectors directly to the CIA Triad. We will examine the categorization of threat topologies, specifically contrasting passive versus active execution. We will then define the structural defense pipeline by drawing a strict boundary between theoretical security policy and implemented mechanism. This methodology establishes the technical foundation required to identify and mitigate various classes of cloud vulnerabilities. Because to properly secure a sprawling, complex system, we must first perfectly categorize exactly how it breaks down. Let's establish the baseline state of a network, a secure, uninterrupted data flow from a source node to a destination node. The first attack vector against this baseline is interruption. This targets the system's availability. A common example is a DOS, or denial of service attack, which is a malicious attempt to disrupt a targeted server by overwhelming it with a flood of internet traffic. This diagram illustrates an interruption. The communication path between source and destination is severed. Below this, we see the second vector, interception. This compromises confidentiality via unauthorized observation, like packet sniffing, the practice of capturing and logging traffic that passes over a network. During an interception, the original data flow continues unimpeded, making the intrusion difficult to detect. This diagram shows the third vector, modification. An attacking node sits directly between the source and destination, altering data in transit to compromise integrity. The final vector is fabrication, where the attacker injects a false data stream directly to the destination, breaking authenticity and integrity. Regardless of a threat's complexity, its mechanical execution maps mathematically to one of these 4 geometric disruptions. These theoretical vectors are operationalized through specific classes of threats. This slide details those primary threat classes: disclosure, deception, disruption, and usurpation. These threats divide into 2 fundamental categories based on whether they alter the system state, starting with passive attacks. Passive attacks, like traffic analysis or the release of message contents, simply observe. Because they do not alter the system state, they are practically invisible to standard detection tools. Since detection is difficult, the primary defense against passive attacks is prevention, primarily executed through robust encryption. Active attacks involve the explicit modification of data streams or the creation of false streams, such as a masquerade. A masquerade is an attack where one entity pretends to be another. Because active attacks change the system state, defense strategies must pivot. Protection here relies on rapid detection protocols and systemic recovery capabilities. Classifying an attack as active or passive dictates how engineering teams allocate their resources, choosing between prioritizing encryption layers or intrusion detection systems. Building a secure architecture requires us to separate the rules of defense from their implementation. This slide distinguishes the 2 concepts. A security policy unambiguously defines allowed system states, establishing what security means. The security mechanism is the hardware or software designed to enforce that policy. Discrepancies between policy and mechanism create actionable vulnerabilities. We can visualize how mechanisms map to policies using set theory. A broad mechanism allows reachable states outside the defined secure states, creating a structural gap attackers exploit. Conversely, a precise mechanism perfectly aligns reachable states with allowed secure states. Modern cloud breaches frequently occurred in the mathematical delta between a strict theoretical policy and a broad mechanism. We apply these models to the real-world shared responsibility model of cloud computing. Cloud security serves as the outer boundary, safeguarding infrastructure and networks from external disruption. Data security forms the inner boundary. It protects the payload through classification, access controls, and pseudonymization, replacing identifiable information with artificial identifiers to maintain privacy. We rely on the operational trinity of prevention, detection, and recovery. Prevention stops attackers from violating policy. Detection utilizes intrusion detection systems to monitor traffic and catch active attacks early. Recovery covers the forensic analysis and system restoration necessary to survive a compromise. A system's resilience is measured by how prevention protocols hand off to detection and recovery during an attack. Threats execute through active or passive attacks, correlating to the disruptions of interruption, interception, modification, or fabrication. These attack patterns compromise availability, confidentiality, or integrity. To defend against them, engineering teams must design precise mechanisms that eliminate the vulnerabilities found in broad systems. In a shared, multi-tenant world, assuming security by default creates a significant operational risk for an organization's most sensitive data. Trust in the cloud is not assumed. It must be rigorously and mathematically architected.